All right, so we're on to RL circuits. Oh, sorry, RL circuits. And what I first want to do is just talk about the FIFE equation and how it applies to the RL circuit. But I guess the best way to do that is to just go ahead and rederive it, since that's what I did in the previous case for the... Oh my gosh, I'm just on the wrong tool here. For the RC circuits, this is exactly what I did, so I'm just going to go ahead and do it for the RL circuit as well. I'm going to try and go fast so that this video doesn't take too long, and again, I don't expect you to necessarily know how to do this. This is a differential equations. You probably haven't taken that course just yet, but what I'm going to do is I am going to have an RL circuit. An RL circuit, just like an RC circuit, is a first order circuit. It has one energy storage element, and that is the inductor. And so if I go ahead and just write the KVL around my loop, I'm going to come up with this expression which says that the input voltage minus the drop across the resistor minus the drop across the inductor is equal to 0, okay? And let's say I have some current flowing in my circuit, well, then I could say that the voltage drop across the resistor is just equal to I times R, right? And then the voltage drop across my inductor, which we learned previously by the IV characteristic of the inductor, is that the voltage is equal to the inductance multiplied by the rate of change of the current with respect to time. So I can go ahead and write that just like this. Well, just notice that this IL is the same. That IL that's going to flow through the inductor is the same as I. So what I'm going to do then is I'm just going to, instead of keeping two different variable names for the same quantity, I'm just going to change I here to IL as well, because that same current that flows through the inductor is going to be the current that flows through the resistor, okay? And so now I can just say that all this is equal to 0. I'm going to do a little bit of a rearranging here. I'm going to say VI minus IL times R is equal to L DIL dt. And then let me just go ahead and shrink this so that I can give myself a little bit more room. Okay. I'll keep going. I'll divide over to the other side in L. So I get V in minus IL times R, the whole thing divided by L, is equal to DIL dt. And then what I'm going to do lastly is I'm going to factor an R over L out of this left-hand side. That might seem counterintuitive, but or not counterintuitive, but maybe seem pointless, but you'll see why I do that later on in the problem. I'm going to factor out an R over L, and then I'm left with a VI that I have to now divide by R to keep, basically to cancel the R that I just factored out, minus IL. And that's going to be equal to DIL dt, okay? And so now I can basically pull this term here over to the other side with the DIL dt, and I'm going to do that. So I'll have R over L on one side is equal to 1 over VI over R minus IL DIL dt. If I multiply both sides by -1, I would actually get minus R over L is equal to 1 over IL minus VI over R DIL dt. And then I can multiply both sides by dt, and I get minus R over L dt is equal to 1 over IL minus VI over R DIL, okay? And then the one last thing I'm going to do to prep this problem, and this is another thing that might not seem particularly intuitive, is that I'm going to rewrite this left-hand side. Instead of R over L, I'm going to write it as 1 over L over R. And again, you will see why I'm doing that later as I progress through this math. Okay? So this is what I'm left with. I can now integrate both sides. Again, I don't expect you to know how to do this. This is differential equations, and this is something that I'm almost certain you haven't learned. But what I'm going to do is I'm going to take the integral of the left-hand side with respect to time. I'm integrating from 0 up to some time t. And then on the right-hand side, I'm integrating with respect to current. So I'll integrate from my initial current, ILI, up to some current at the time t, IL of t, okay? And so this is, if you haven't noticed already, shaping up to be very similar to the RC circuit derivation, which is exactly what we would expect. It's just basically the dual component of the capacitor, but the inductor is reluctant to changes in current rather than changes in voltage, which is why everything here is in terms of current. Okay, so if I integrate the left side, I just get negative T over L over R. If I integrate the right side, I'm going to get that this is going to be equal to the natural log of IL minus VI over R, evaluated from ILI to IL of T. Okay, and now I'm going to go ahead and copy this over to here and keep going. So I'm basically just going to continue on here. And I'm going to say negative T over L over R is equal to the natural log of IL minus IL of T. Oh, sorry, I'm plugging in for IL. So it's going to be IL of T minus VI over R minus the natural log of ILI minus VI over R. And then using my log rules, I can rewrite this as a fraction, right? I can rewrite it as IL of T minus VI over R over ILI minus VI over R. And then this is still negative T over L over R. Well, now again, I can go ahead and exponentiate both sides. Put an E here and an E here. These cancel. I'm left with E to the negative T over L over R. You're starting to see patterns here, I hope, from the RC circuit equation. And I get this expression on the right-hand side. I can multiply both sides by this denominator here, and I get that ILI minus VI over R times e to the minus T over L over R is equal to IL of T minus VI over R. And the last thing I need to do is add this term over to the other side. And then I'm left with IL of T is equal to VI over R plus ILI minus VI over R e to the minus T over L over R. All right? And so the very last thing that I need to do here, let me go ahead and just grab all this and shrink it so I can make some more space for myself. The very last thing I need to do here is I need to recognize that this VI over R in my circuit, if my inductor behaves like a short, then this voltage here is going to be 0 volts. And so my current, my final current, once this circuit is in steady state, is going to be equal to VI minus 0 over R. So I can actually rewrite VI over R as my IL final, right? And that's exactly what I'm going to do. So I'm going to rewrite this expression as IL of T, oops, let me go to the black. IL of T is equal to IL final plus IL initial minus IL final e to the minus T over L over R. And this L over R is my tau for an RL circuit, okay? And this is my expression, and we are done. We've derived the FIFE equation for the RL circuit, and it is in the exact same form as it was for the RC circuit. This video might have gotten a little bit long, so I apologize for that, but I just wanted to get through this derivation. Just want to get through this derivation. I think it's important to show where these equations come from. Of course, I'm just going to reiterate this one more time. I don't expect you to know how to derive this. I will expect you to know how to use the FIFE equation for RL circuits to determine the current, similarly to how we used it for determining the voltage across the capacitor in the RC circuits. Okay, so without any further delay, this video has already been pretty long. I'm going to go ahead and move on to the next video.